Sorry for the interruption. Total vertical load at pulley C. Total vertical load at pulley C is now T1 plus T2 sin 60 plus WC. If I do that, I will get. Now please do the simple calculation at home later. Now I'll just give the final solution here. I mean Newton. That is downward. So total vertical load at pulley C is T1 plus T2 sin 60 plus WC. WC is 1000 Newton. Already we have calculated T1 and T2. We know T1 and T2. So what is T1 plus T2 sin 60 plus WC? It will be 8,929 Newtons. Okay. Similarly, total horizontal load at pulley C. Total horizontal load at C, at pulley C is T1 plus T2 cos 60. Cos 60, horizontal component, cos 60, it will be 4,578 Newton. Okay. So this is total vertical load at pulley C, 8,929 Newton. Total horizontal load at pulley C is 4,578 Newton. Next we will go to gear D, analysis of gear D. So let us analyze now gear D. Pulley C is over. Gear D. Analyze gear D. Analyze gear D. Analyze gear D. So this is gear D. Shaft to be designed. Gear D. This is driver. Driver gear D or pinion. Normally driver is always called pinion. What is called as pinion? D. Pinion D. Now this gear will drive another gear located in front of it. Already we have discussed about this. As viewed from the right hand bearing, this gear will drive another gear that is located in front of it. Now whatever the power that has been received by the shaft, now it has been delivered through a gear. Okay, and this gear will drive another gear that is located in front of it. Now, what is the direction of rotation of the gear? Clockwise. Already we know that because the shaft is rotating in clockwise direction. Because this is driven gear, because this is driver gear, the direction of the tangential force always act in the opposite direction as that of the rotation of the driving gear. It all depends on whether we are analyzing driving gear or driven gear. In this particular problem, we are analyzing driving gear. The direction of the tangential force, FTD, F suffix TD. So the direction of the tangential force FTD will always act in the opposite direction to that of the rotation of the driving gear. Of course, the radial force will always act in this toward the center of rotation of the driving gear. Now this is the convention. In case if you are analyzing driven gear, the direction of the tangential force will always act in the same direction as that of the rotation of the driven gear. Of course, the radial force will always act toward the center of the driven gear. Is it clear? Now in this particular problem, because it is a driving gear, since the shaft is rotating in clockwise direction, the direction of the tangential force FTD will always act in a direction opposite to the rotation of the driving gear, and the radial force FRD will act toward the center of the driving gear. So toward the center, this is FRD. Of course, this is your reaction here. Reaction R, that is the resultant. Reaction R, this is your alpha. Alpha, what is alpha? Pressure angle. Now how to find out FTD? FTD is nothing but TD by RD. RD is already known because diameter of the PCD how much? It is 200 millimeter. So what is RD? RD is 200 by 2, 100 millimeter. 100 millimeter. RD is 100 millimeter. Now if we calculate, what is it? FTD. If I calculate FTD, now it will be how much? 9,550 Newton. Because I know TD. How much is that? 955 to 10 raised to 3. I know radius of the driving gear D, that is 100 millimeter. You just substitute for TD and RD, I will get 9,550 Newton, that is acting in the downward direction. What about radial force? FRD is FTD tan alpha. FTD tan alpha. What is alpha? Pressure angle. I think pressure angle is given here, 20 degree. If it is not given, don't worry. You just assume it. Assume. So normally we assume 20 degree pressure angle. If I solve for FRD will get FRD is how much? 3,470 Newton. You will get 3,470 Newton. Okay. I hope you understood how to find FTD and FRD. I hope you understood how to use the same convention here because we are analyzing driving gear, because the gear that is mounted at the shaft is a driving gear. The direction of tangential force will always oppose the rotation of the driving gear, and radial force will act towards the center of the driving gear. If we solve for FTD, we'll get 9,550 Newton. Solve for FRD, FTD tan alpha, you'll get 3,470 Newton. Now total vertical load. Now let us calculate total vertical load at gear D. So let me calculate total vertical load at gear D. So if we calculate total vertical load at gear D, total vertical load at gear D, total vertical load at gear D is equal to, I think around, because the weight of the gear D is there. This is WD. That is there, WD is I think 400 Newton. It is given in the problem. If I find out the total vertical load FTD plus WD, we just add these two, I think you will get around 10,050 Newton. Now please do this problem at home. You practice this later. Okay, total vertical load. Similarly, total horizontal load at D is equal to FRD. That is FRD only. This is downward. Please, you have to show the direction. Very important, because when I draw the loading diagram, you must know the direction there. So FRD, that is acting. How much is that FRD? 3,476 Newton. That already we know. So that will be acting towards right. So total, we know now total vertical load at gear D 10,050 Newton, downward direction. Total horizontal load at gear D is FRD, that is 3,470 Newton. Sorry, 3,476 Newton. Okay, now let us draw the loading diagram. So this is over now. We have analyzed pulley C and gear D. I hope you understood how to analyze pulley C. What is pulley C? Pulley C is a driven pulley because the power has been received by the shaft through that pulley. So whatever the pulley that is mounted at the shaft, it's a driven pulley. Now whatever the power that has been received by the shaft will be delivered by means of a gear. So the gear that is mounted at the gear, the gear that is mounted at the shaft design is a driving gear. Now let us draw the loading diagram. We will draw loading diagram. First let us draw the vertical loading diagram, VLD. So we know the reactions. RAV, let us assume this direction of the reaction, RAV and RBV acting in the upper direction. So right now we don't know the direction of these reactions at the supports A and B, but initially let us assume it. Say in the upper direction. In the end we will prove whether it is right or wrong. If it is not correct, we will change the direction. Okay. Now initially let us assume the direction of the reactions at the supports A and B in vertical direction. In upper direction. Okay, reaction. Now what about that gear D? What is the direction? So let me see the loading diagram here. I will just check it. So vertical loading diagram, VLD here, gear 10,050 Newton. Already we have calculated total vertical load at gear D. This is already known. Similarly, total vertical load at pulley C, that is also acting in downward direction. 8,929 Newton. 8,929 Newton. This is also known. So we know total vertical load at pulley C 8,929 Newton. Correct. And total vertical load at gear D is 10,050 Newton. So reactions RAV and RBV. Now what is that I have to do? So distance, of course. So let us mark this here. I think between the bearing supports here 1100 millimeter, because the length of the shaft is 1500. Out of that you subtract 400. This is 1100 millimeter, and between the gear and the right bearing B, it is 500 millimeter. It is given in the problem because the gear is mounted at a distance of 500 millimeter from the right bearing. That is given, and this will be 600 millimeter. So just now for our convenience, let us do this. And now once I draw the vertical loading diagram, the next thing is that we have to find out the reactions. Now we know how to find out the reactions, taking, say, you can take moment about either A or B. Now anything will do. So let us say taking moment about B. So that is, what is moment about B? RAV. So clockwise movement, let us take clockwise movement, positive, anti-clockwise movement, negative. What is moment due to RAV about B? RAV into 1100. RAV into 1100, because that is going in the clockwise direction. So moment due to reaction RAV about B is going in the clockwise direction. So it is RAV into 1100, that is plus RAV into 1100. Now what is moment due to 10,050 about B? That is acting in the anti-clockwise direction. So moment due to 10,050 about B is acting in anti-clockwise direction. So minus 10,050 into 500. Then what is moment due to 8,929 about B? That is going in clockwise direction. So plus 8,009 from here to here, this 400. It's already there. The problem. Plus 8,929 into 400 should be equal to 0. You know that algebraic sum of the moment about B should be equal to 0, total. Okay, algebraic sum of the moment about B, sigma MBV should be equal to 0. Algebraic moment due to all the vertical forces about B should be equal to 0. So what is moment due to RAV about B? Plus RAV to 1100. Why it is plus? Because it is going in clockwise direction. Because that is the convention we have used. Clockwise positive, anti-clockwise negative. What is moment due to 10,050 about B? Minus 10,050 into 500 because that is going in anti-clockwise direction. And what is moment due to 8,829 about B? It is plus because it is going in clockwise direction. 8,929 into 400. If I solve for RAV, so let me solve for RAV. If I solve for that, 1 minute, I will get RAV is 1321 Newton. I think, let me check it here. I think we have done that. RAV, I am getting 1321. 1321 Newton, that is plus only. I am getting plus. Plus means whatever the direction I have given here, I have assumed initially that is correct. I have assumed RAV acting in the upper direction. So whatever, because I am getting positive sign here, so the direction is okay. So I need to change the direction. Suppose if I get negative value here, then in that case we have to change the direction. Because in this case we are getting positive value, so we don't have to change the direction. So RAV will remain upper. So 1321 Newton. Similarly, suppose if we how to calculate RBV? No, we can find out RBV again by taking moment about A. Algebraic moment due to all the vertical forces about A should be equal to 0. We can do that. Otherwise, you see, this is more convenient. Instead of taking moment about A, we can just take algebraic the forces should be equal to 0. We can apply the condition for force equilibrium. Instead of applying condition for moment equilibrium, you apply the condition for force equilibrium. Upward force positive, downward force negative. In that case, what is here? RAV upward force positive plus RBV. RB both are upward here. Minus 10,050 downward, that is acting in the downward direction. Minus 8,929 should be equal to 0 because this is more convenient. Otherwise, that is more laborious, more tedious. Okay, it will take more time. If you see, that will also do. Taking moment about A also we can do, but instead of that we can do this. Taking algebraic moment, algebraic force should be equal to 0. Upward force positive, downward force negative. When I solve for RBV, I am getting 17,658 Newton. Around 17,658 Newton. Anyhow, please check these values at home because I have only solved this problem. Anyhow, you better check it whether it is correct. So please do these problems at home later. So okay, this is RAV and now we have found out RAV 1321 Newton plus 1321 Newton. RBV is also plus 17,658 Newton. It means that both are acting in the upper direction. Both are positive. Okay, once I find out reactions RAV and RBV, what is the next thing I have to do? I have to take the moment. I have to find out the moment. So let us find out the moment. So let me find out the moment. So bending moment. Let us find out bending moment. What is bending moment? End point. Please remember, bending moment at the end point will always be 0. Irrespective of the problem. Always. Bending moment at the end point will be 0. That is MAV is equal to MCV equal to 0. This is C. This is C. Correct? This is C. This is D. This is D. So bending moment at the end point MAV, MCV equal to 0. Now what is bending moment at D? MDV. So if I want to find out bending moment at D, I can find by taking moment due to all the forces either to the left of the point D or to right of point D. Anything will do. So whichever is convenient we can do. In this problem, because there is only one force to the left of point D, it is easy for me to find out moment due to RAV only because there is only one force to the left of point B. If I want to find out moment due to all the forces to the right of point B or point D, in that case there will be two forces. One 8,929 Newton that is acting at point C and RBV here that is reaction at support B. Now both we have to take there. So we have to find out moment due to 8,929 Newton and also moment due to RBV. So that is somewhat okay tedious, more tedious than this taking moment due to because there is only one force to the left of point D, point C. Because there is only one force to the left of point C, it is easy for me to find out moment. So that is nothing but RAV into 600. So that will be bending moment at point D. If you find out bending moment at point D, I think, where is that? Bending moment at point D, I am getting just 0.79. 0.79 into 10 raised to 6 Newton millimeter. Is it not? No, you will get the same answer if I take moment due to 8. What is that? For example, if I want to, what is moment due to 8,929 would be? That is 8,929 into 900 minus RBV, that is 17,658, something is there, into 500. If I do that, I will get the same answer. I'll get the same answer. So what is bending moment at point D? That is 0.79 into 10 raised to 6 Newton millimeter. Now what is the direction of that moment? Because we are applying force here, reaction. Because of that reaction RAV, there is bending moment at point D. In which direction that reaction is acting? It is acting in the upper direction. Because of that, what will happen? It will bend in this direction. It will bend in this. This is sagging. Sagging. So we have to call it a sagging moment. Sagging moment, because when I apply reaction here, RAV, it will bend like this. At point D, the shaft will bend in this direction. So if it bends means that is sagging. So sagging moment. So sagging. Similarly, then if I want to find out what is bending moment at point B, in the same way we can argue bending moment at point. See, we can find out bending moment at point B by taking moment due to all the forces either to the right of point B or to the left of point B. Because there are two forces to the left of point B, so it will take more time. Instead of that, because there is only one force to the right of point B, it is easy for me to find out bending moment due to 8,929 only. So what is bending moment at point B? So that is 8,929 into 400. 400, how much is that? 8,929 into 400, that is 3.57957 into 10 raised to 6 Newton millimeter. Now what is the direction of that moment? It is hogging, because we are applying force in this direction like this. You see, we are applying at point D. This is point D. This is point D. Now we are applying force 8,929. No, please see here. I am applying force 8,928 Newton like this in this direction. So it will bend like this. It will bend because of that force 8,929 Newton at point D. The shaft will bend in this direction. It is hogging. It will go like this. Hogging. This is hogging. So let us call it as hogging. Okay. Hogging. Okay. So now I have found out bending moment at each loading point here. I hope you understood what is bending. So please note at the end point always. At the end point, bending moment will be 0. So MAV is equal to MCV equals 0. And MBV is RAV into 600. Because there is only one force to the right of point C, it is easy for me to find out bending moment due to RAV. Because only RAV is there. RAV into 600, that is 0.79 into 10 to the 6 Newton millimeter. That is sagging because it is upward. It is going like this in this direction. So in that case, it will bend like this. So the shaft will bend in this direction, that is sagging. Similarly, what is bending moment at point D? It is nothing but 8,000 because there is only one force to the right of point D. Point B, we can find easily if we can find out bending moment at point B due to 8,829. That is 8,829 into 400. I am getting around 3.57 into 10 raised to 6 Newton millimeter. But it is acting in the downward direction, so it will bend like this. So the shaft will bend like this. This is hogging. So I hope you understood. Now, once you find out that, the next thing is that you have to draw the bending moment diagram. So I have to draw the bending moment diagram. So if I draw the bending moment diagram, so you don't have to take any scale. Approximately you can draw this bending moment diagram. So don't have to take proportionate, you can just draw the bending moment diagram. You think we have drawn the bending moment diagram here. So vertical bending moment diagram. We call it as vertical bending moment diagram, VBMD, vertical bending moment diagram. At the end point it is 0. Now here it is around 0.79 into 10 raised to 6. So just approximately I am showing, I am not taking any scale here. Just proportionately I am drawing. At point B it is 3.57 into 10 raised to 6. Okay, just you join this like this. Okay, so this is the shape of the bending moment diagram. Okay, this is VBMD, vertical bending moment diagram. Now similarly, next we will draw the horizontal loading diagram.